Hello, today I will talk about a new topic in machine learning called logistic regression, and I will start as usual with the idea and theory behind it. So suppose we have a group of persons with certain features that we need to learn or to predict, and we have some training data about those persons that can tell us certain facts about their characteristics. In the linear regression videos, I talked about how we can deal with features like the heights and weights of a group of persons, such that if we obtain certain values of heights and weights, then we can use these features in order to build a linear regression model, for instance, such that if we have a new person where we only know his or her height, then we can use this linear model in order to predict his or her weight. But there is another type of variables that I haven't talked about it before, which is called the discrete or categorical variable. Such variables have another way of treatment because it doesn't have a continuous numerical form like the heights and weights, but it has rather discrete values, or more or less a certain finite set of classes or categories that can describe the whole population of your data. So here, for instance, if we have this data about a group of persons, we can classify this group of persons into two categories, one for females and another one for males. So this is another type of data that we need to deal with using a classification method like regression, like logistic regression. Usually the numerical continuous variables like the height and weight, we call it quantitative or continuous variables. But the categorical or discrete values like the gender, for instance, we call it a discrete variable or categorical variable. And we have a lot of examples around us of categorical variables, which contains a finite set of outcomes or a finite set of possibilities against each feature. Like, for instance, the gender, we can express it as either female or male. The marital status, we can classify it as single, married, divorced, or widowed. The power switch can take either on or off cases. The exam result can be pass or fail, and so on. So we have a lot of examples around us of categorical variables that we can classify using machine learning algorithms like the algorithm I am talking about today, the logistic regression. So the first pre-processing step we need to do is to do some sort of encoding of this categorical variable because in order to insert it to our machines and do some certain computations on the categorical data, we need to set it to certain numerical values. So in our example today, I will set the female to 0 and the male to 1, such that we can have a numerical representation of this discrete variable, and we can deal with it in our machines computationally. The second step we need to do is to visualize our data. So here I am giving you two plots, one for the height variable against the weight variable, so two continuous variables, and here I am giving you the set of height variable against the gender a variable, setting it to 0 or 1 for females and males. And as you can see here, that here we have a certain degree of correlation which we have built upon in the linear regression tutorial, and we managed to find certain function that can express the relationship between these two continuous variables, the height and the weight. We managed to find a linear function like this one that represents such relationship. But in case of classification problems like the one we are talking about today, we need to think in different way about the relationship. The main point or the main aspect that we need to take care of when we search for a function that can represent or that can classify a set of data into two classes like females and males, we looking for a function or a hypothesis that generates values between 0 and 1. And the reason for that is that we need an outcome of our model that can be converged to either one class or another. So we can say that if our classification model generates a value, for instance, between 0 and 0.5, then we can round it to 0 and we can say that this candidate or this person is more likely to be a female rather than a male. And if the generated outcome is above 0.5, so between 0.5 and 1, we can say that this person is more likely or more probably to be a male rather than a female. So in other words, we are looking for a probabilistic classification function, or a function that generate a probabilistic values between 0 and 1. So how we can find such function? We will start by the simplest function we can use, which is the linear function. So here I have computed the regression function between the height and the gender, and I found that the best fit lies within the definition of this function. It is equals the hypothesis equal 0.08 multiplied by the height, our predictor, minus 4.65. So in other words, as I mentioned to you, that we looking for a probabilistic function. So we instead of calling the hypothesis f of x and w, we called it the p, which is abbreviation of probability, that the gender equals 1. And the idea behind this definition is that we are looking for a function that gives us the probability that the outcome will reach its maximum value of 1. So for instance, if the probability of gender equals 1 generate a value of 0.7, we say, okay, we have the 70% chance that this candidate is a male. If the outcome is 0.3, we will say that, okay, this candidate has a very low probability to be a male, and accordingly very high probability to be a female, and so on. So we always express our hypothesis in the classification problems with the probability of gender equals 1, or the probability that the outcome will reach its extreme. And we build upon this understanding. So let's have an example of a new observation or a new person with his or her height equals 65 inches. When we compute the corresponding linear function, we will find that the generated value equals 0.08 multiplied by 65 minus 4.65, which is equal to 0.55. So we interpret this outcome as that this new candidate has a 55% chance to be a male and a 45% chance to be a female. This is how we interpret the outcomes of our classification problem, or of our classification hypothesis. So let's take another example. Let's assume that we have a person with his or her height equal 57 inches. When we compute the corresponding linear function, we will find that the outcome equals minus 0.09. Actually, this is an unaccepted value in terms of the classification problem, because as I mentioned before, we are looking of a function that generates values always between 0 and 1, and as this linear function generates value below 0, then we cannot accept this linear function as a proper classification model of our problem. As another example, if we take a person with height equals 75 inches, we will find that the outcome of the linear function equals 1.33. Again, it is not accepted value because it exceeds the extreme value of 1, which means that it is not a probabilistic value, and accordingly we cannot accept this function as a classification model of our problem. So we conclude that the linear function is not a suitable function for our classification problem. Secondly, we will try to use another sort of functions called the Heaviside or step function. And the nice thing about the Heaviside or step functions is that we can divide it into multiple domains, such that we can guarantee that the output of this function is always equals or between 0 and 1. So for instance, here we have two values of predictor height, A and B. At domain before A, if the height is below the value of A, we set all of the outcome of the function equals to 0. And if the height greater than or equals to the value of B, we will consider all the values of the generated outcome equals to 1. And if the value is between A and B, we will still use our regression value, which is guaranteed in this case to generate values between 0 and 1. So using such a definition, we can guarantee that the output of this step function will generate values between 0 and 1, or in other words, it will generate a probabilistic values. So this is the advantage of the Heaviside or step function, that it is guaranteed to generate a probabilistic outcome. However, we have a drawback of this sort of modeling, which is this sort of functions are not a smooth function. And smoothness is a very important concept in any function we use in our regression models. And by smoothness, we mean that the function that you are looking for must be differentiable over every point of its domain, which means that we need a function that we can have a true value of its first derivative in each point over its domain. And as you can see from the definition of Heaviside function, is that we have 3 domains of this function, and for 2 of these 3 domains, the function equal to constant. So from minus infinity to A, the function equals to 0, and from B to plus infinity, the function equals to 1, which means accordingly that the first derivative over these 2 domains will equal to 0, and this is not a good selection of a regression model, because you know that afterwards we need to optimize this function, and we need to calculate the derivatives of this function in order to find a good values of its coefficients. And in this case, we need a smooth function, which is not the case with Heaviside or step functions. So we conclude that also the step functions are not suitable for our classification problem. Our third choice is the logistic function, and actually we can see from the characteristic of the characteristics of the logistic functions is that this class of functions can be very suitable to the classification problem. It is defined as the probability that the target value variable y super I equals 1 divided by 1 plus e, the Euler number, to the power of minus f of x super I and w. This is the mathematical definition of the logistic function, and it has a very nice properties that suits our needs in the classification problem. It is probabilistic, which means it always guaranteed to generate values between 0 and 1, and it is continuous, which means it is not discrete in any point of its domain, and also it is smooth, which means it is differentiable over each point of its domain. So this is the basic features that we are looking for in order to represent our classification problem. So we decide that the logistic function is the best function for this sort of problems. Now I want to explain a little bit about this term over here, which is the function of x super I and w. This function here is nothing but a linear function over one or more than predictor from x1 to xk. So it can contain a single or multi predictors, depends on the data you have. And we can also represent this linear function into a more vector form or more compact form by multiplying the vector of coefficients by the vector of, or the matrix of predictors, then such that we have a more compact form which is called the W transpose X. And we can also rewrite the logistic function using this new vector notation of the linear function. So we can say that the probability of y equals 1 divided by 1 plus e to the power of minus wtx, or W transpose X. Now, as you can see from the definition of the logistic function, is that the probability of y equals 1 has a non-linear relationship with the predictor x, or we call it that it is some sort of non-linear transformation of the linear function W transpose X. So the question would be, is there some linear interpretation that we can have between the target discrete variable y and the set of predictors x? And the answer to this question is yes, we can have such interpretation using a very fundamental concept with the theory of probabilities called the odds concept. And the odds value is nothing but the ratio of the probability that a given event is going to be happened divided by the probability that this particular event will not going to be happen. So we can say if our event is flipping a coin, we can say that the odds is the probability that the outcome will be a head divided by the probability that the outcome will be a tail, for instance. So this value can be represented as the probability that y equals 1 divided by 1 minus the probability that y equals 1 again, because you know the probability that the event will not occur equals 1 minus the probability that the event will occur. So we can write it in both cases, are both definitions are valid definitions. So by using the above definition of the probability of y equals 1, we can rewrite the odds expression as 1 divided by 1 plus e to the power of minus wtx divided by 1 minus 1 divided by 1 plus e to the power of minus w transpose x. We will insert this one, insert the fraction by translating it into 1 plus e to the power of minus wtx divided by the denominator will give us 1, minus 1 divided by the same denominator. Then we will delete 1 against minus 1, so we will end up with this expression divided by e to the power of minus w transpose x divided by 1 plus e to the power of minus w transpose x, which is equal to the first term, and we will flip the numerator and denominator of the second fraction, and we will flip the division into multiplication sign. Then we will end up with this expression, and as you can see that the term here will delete the term here, and we will end up with the odds of this logistic function equals to 1 divided by e to the power of minus w transpose x, which is again simplified to be e to the power of w transpose x. So actually, still within the this definition of odds ratio, we didn't come up with a certain linear relationship between the target variable y and the predictor x. However, if we take the logarithm of both sides, we can say that the logarithm of odds equals the logarithm of the value on the right hand side, the e to the power of w transpose x, and the logarithm will remove the Euler value, and we will end up with the expression w transpose x, and in this case we call the ln of odds, we call it simply in the simple word, or in one word, the logit of y. Now we have a linear relationship between not exactly the target variable y, but with the logit of y with the linear function of predictor x, which is represented by this form here. If we have the predictor x here and the logit of the categorical target variable y, then we can represent the relationship as a linear relationship defined by the linear function w transpose x. So this is the idea and the theory behind the logistic regression, and in the next video I will talk you about how we can compute the cost function of this model. So thank you so much for your time.